And I've recorded the first session, Sarah, so I'll share that with you. Oh, good. We have someone else just joining. Zara just joined. I think Zara may be from, let me just check. I'm going to quickly do some. Oh, can ask Zara. Okay, so so the thing that says 120 ROR is stands for 120. ROR is read out room. So this is where we would be sitting if we were at the telescope. And Stephanie was a UCSC undergraduate, 4th year. So there you are, you can see her on the camera. She's actually in person at the telescope. And Sean Stone, who's operating the telescope tonight for us, is also in the readout room. There's Sean. Hey, Sean. So Sean and Stephanie are at Mount Hamilton. Stephanie drove up in the afternoon. Is going to spend the night there. Sleep in the morning after nights observing. Kevin McKinnon is a PhD student at UC Santa Cruz. Stephanie is a 4th year undergraduate at UCSC. This is part of her senior thesis. Stefan Kimura is a post-bac student who's based in Kona in Hawaii. He did his undergraduate degree in the mainland in Willamette in Oregon, if I remember correctly. Rafael Nuñez is also post-bac. Did his undergraduate degree at UCSC. And I'm Raja. We are the science team. Actually, there's at least one other person in the science team. Who else am I missing? Chun Siu is at Keck now, and Monika Soraisam is not on this call. She's based in Hilo. So we're a big team that got time on the telescope. Oh, there you are, Stefan. Hi. Let's see. Lafika, which town are you in Botswana? Are you in Botswana? Did I get that correct?
Hello everyone. Hopefully I'm audible.
Yes, we can hear you.
Okay. I'm in Botswana, in the capital city, Gaborone. I'm in the University of Botswana here.
Oh, fantastic. Fantastic. Thank you so much. Did you heard about this from Gihan?
I heard about this from my mentor, Dr. Monika Nyitsipa.
Dr. Tsiba. Okay.
Yes, he couldn't make it, or he said it was going to be late.
No problem. We'll be here for a while. He'll be here. Welcome. And tell us a little bit about yourself. Are you, do you study or teach at the university? There's Sarah.
I am currently doing my MSc here.
Oh, fantastic. Okay.
I'm studying nuclear structure physics.
Sorry, say that again, please. You're studying?
Nuclear structure physics.
Okay, nuclear structure. I see.
No.
Thank you so much for joining. And Sarah, thank you for the introduction in the chat. So you're with the planetarium. Okay, fantastic. Zara, thank you. You're a senior in high school in Botswana. Thank you so much. Okay, for joining. And Sarah, what does NAEC stand for, please?
Sorry about that. So it stands for National Astronomy Education Coordinator, which is it comes under the Office of Astronomy for Education, which is part of the IAU. They've set up.
Okay.
Yes, the OAE. Yes.
OAE.
So there's a team of 3 of us representing Ghana, if you like, for the OAE.
Fantastic. And which city are you based in?
Accra, Ghana, capital of Ghana. Accra.
Ghana, okay.
Yeah.
Fantastic. This is an important beginning for us tonight, beginning of sorts, continuation of another sort. I say beginning because we have a special phase of the program that kicked off on August 1st, and tonight is the first this is the second session, but tonight we've had two. Tonight is the first time we're on the telescope since this special phase started on August 1st. I say special phase because we've been funded by a foundation to run this program, the Heising-Simons Foundation, to run this program for the next 3 years. And so delighted, and this is really our first time connecting with students and educators from Botswana. So we're very happy to be to make this connection. And this has come about through Vicky Newberg, who's a teacher in Hawaii who spends her summers in Maun in Botswana. Am I saying Maun correctly? M-A-U-N?
Yes, you are.
That's how it's pronounced. Okay. Okay. So yes, a teacher in Hawaii has helped us make this connection in Botswana. We're a small group, and please feel free to ask us questions. And we're recording this session, but feel free to ask us questions that you might have about the experiment we're doing. I will actually turn it over to the science team, rest of the science team, to see if they would please explain what, we're seeing a spectrum of a star. Let me make a weak attempt at this. So we're seeing the spectrum of a star. That's what you're seeing in, if you, I guess you can't see my cursor, but in the upper part where this long rectangle is, yeah, you can see the cursor there. Okay, that's a spectrum of a star. That horizontal streak going across is the light of a star, and what is running across from left to right in X is wavelength. It's changing. A wavelength is increasing from left to right. So in the center, in the right edge of that rectangle is where green light is landing, and of the Roy G. Biv of the rainbow. So the violet, indigo, blue, and green is what we are. Is that part of the star spectrum that we're seeing? We're actually looking slightly into the ultraviolet as well, near where the cursor is now, near the left edge. And things sort of peter off to the left because the Earth's atmosphere absorbs a lot of the ultraviolet. The stars don't put out that much ultraviolet, and our whole system, our camera, charge coupled device, all of these things are not very sensitive in the ultraviolet. So that's why you sort of see this fall off. You can't see the streak from the star too far to the left. You can see it in most of that rectangle, but not all the way in the left. So this is something called a double spectrograph, where we take the light of the star, split it up into two broad bins. Everything that's shorter wavelength than green light goes into this camera. And then there's another camera into which all the wavelengths that are longer than green light go in. And this one is displayed vertically instead of horizontally. And now green light lands at the top. And then what comes beyond green is yellow, orange, red, the beginning of the infrared. That's what you're seeing over here, with wavelength increasing, with increasing Y coordinate from top to bottom. Sorry. There are various controls here. These controls are something we would see if we were at the telescope on the mountain, but we would also see them in this mode if we were operating it from home on our laptop. So that is what gives us the opportunity to share our screen. I'm going to put some names, the project name in the chat. We are running a project called Salvation. It's an acronym. It stands for Spectroscopic. I'm typing this into the chat. And I type very slowly, especially at the time of the night. And Stephanie and others on the team, this is not an M31 transient yet, or is it? Or
This is an M31 variable.
Okay. So this particular thing that we've got a spectrum of is a star in the Andromeda galaxy, so located about 2.5 million light years away. And the name of our project is Salvation. It's the acronym. I spelled out what it stands for, spectroscopic analysis. That means we're using a spectrum to understand the object, to understand its temperature, its chemical composition, how fast it's moving, what kind of object it is, what kind of star, or if it's an exploding star, what kind of object it is. So spectroscopic analysis, that's what those two words mean. We're splitting the light into the colors of the rainbow and using that information. But the things we go after are stars that are intrinsically very luminous, but they vary in brightness. That's why they're luminous variables. And transients are things that appear out of seeming nothingness. There was nothing there, or whatever was there was too faint to be seen before. Now it's suddenly seen, and then it may disappear again. If it's an exploding star, you only see it during the explosion, not before or after. And so a transient is something that varies by such an extreme amount that it only is visible for a short period of time and not at other times. Sometimes that'll repeat. So those are recurring transients. But a variable is something that goes up and down in brightness but is visible to the telescope at all times. And in our neighbor refers to the Andromeda galaxy, which is our neighboring galaxy. So our neighboring big galaxy is 2.5 million light years away. So the light we're seeing is that old. It's been traveling for that long. Let me see what else. Okay, so they're taking an exposure that's 500 seconds in length. And you can see that the amount of time that has already elapsed is nearly 300 seconds. And what is left to go is about 200 seconds. You can see that in the elapsed and remaining counter there. And there's one other window that we're sort of using 3 virtual windows to control the telescope. This is the red part of the spectrograph you're seeing now. And now we are moving to the part that helps us guide the telescope very finely through the night to compensate for the Earth's rotation. And you can see a compass rose, north, south, east, west. This is not a mistake. If north is up, east is to the left. On the sky, on the Earth, it's exactly the opposite, but north is up, east is to the right. Because in one case, we're looking at a globe from the outside when we're looking at the Earth. And when we're looking at the sky, we're looking at the celestial sphere from the inside. So that's why there's this parity reversal between how north, south, east, west are drawn on a map of the world versus the map of the sky. What else do you see here? In the thing that says coords, that stands for coordinates. These are, the first column is the ID of the object, but then the second and third column, RA and DEC, are right ascension, declination, equinox of the coordinates, because the Earth's axis isn't always pointed in the same direction. It changes, it sweeps out a cone every 26,000 years. So that's why when we write down the coordinate, we have to specify the equinox or epoch of the coordinate system. This is like RA is like a longitude, DEC is like a latitude. So again, lots of parallels with Earth's geography and how the sky is mapped. Any questions at this point? If anyone wants to chime in
Sure, I'll add a couple more things. So yeah, the goal of this project right now, the particular object that we're looking at this time is, as we said, a variable star in Andromeda. And so there's kind of 2 parts to Salvation. The first part, which was happening earlier in this night, was where we go after transients. So these things that'll appear in the night sky where there didn't seem to be anything before. And a lot of what we're doing in that project by collecting spectra is trying to figure out what type of object it is. And it's especially important for something that might disappear in a few weeks in terms of being too faint for us to pick up with our telescopes anymore. And so in a lot of these cases, we're looking for particularly rare events that don't happen very often. And so if we find something particularly exciting, we have some methods to tell the rest of the community, hey, we found something interesting. And if you have time on telescopes and you're interested in this, you should also look at it too. So that's that's one thing that we do. But right now we're on to the other part of the Salvation Project, which is studying variable stars. And so these are stars whose brightness tends to change in a periodic way. So like maybe like a sinusoid or some other functional form. And while some of these types of stars are well understood in terms of us being able to model the physics, that isn't always true for a lot of the stars that we are trying to understand. There's a lot of recently discovered and not well understood types of stars whose brightness changes over time. And so what we're doing is we're collecting spectra at multiple times throughout that brightness fluctuation to see if we can learn about the physics inside of these stars. And so as Raja said, by collecting a spectrum, and maybe I can kind of find an example here. No, I'll go back to a much brighter spectrum. Let's see, this one. Oh, how about that? Okay. So if we look at a spectrum of a star like this one here, this is a very bright star. What you notice, first of all, is that there's kind of a general shape here. And the general shape that you see tells you a lot about the properties of the star. So things like its temperature is kind of the main thing that we get out of that. But also what you'll notice is that there are these bumps every now and then, or these dips. And if I zoom in on this, you see this strong feature here. This particular feature, I believe, is caused by hydrogen in the atmosphere of the star. So as the light is passing from the center of the star, it passes through kind of the diffuse outer layers of the star. You can think of it as like the atmosphere of the star. And in doing so, it interacts with the elements that are present in the atmosphere of the star. And so the chemical signatures of those elements ends up in the light that reaches us. And so we can do a few things by seeing a feature like this one. One, we can confirm or deny the presence of a particular element. So this is caused by hydrogen, but there are other ones that are caused by iron. There are other ones that are caused by calcium. The other ones that are caused by magnesium. And so we can use the strength of this feature to measure how much of a particular element there is. We can also, by measuring the location of where we observe this feature versus where we know it should be in a lab, we can use that to measure how fast the star is moving towards us. We can also measure the amount or basically the shape of this feature to help us understand the temperature and the pressure, as well as the rotation speed of the star. There's so many different properties that we can learn by taking a spectrum of a star. And so those are some of the main things that we can try to measure.
So Kevin, if you go to that spectrum just one more time, please. This is it's really lovely that it's, okay. So this is a different object, is it? Or is it the same one?
No, it's the same one. It's just hard to get
card.
aligned.
Right, got it. Okay, so what is really beautiful about this is you can see H beta really clearly at 4861. Then that's, so this is exactly as Kevin said. This is, so, we study quantum mechanics in college and university. The same quantum mechanics that's happening on Earth in our laboratories is also happening inside stars. This is the beautiful universality of these phenomena. So hydrogen atoms in the outer layers of the star, in this, what Kevin is saying, the atmosphere of the star, what they do is they absorb the light that's coming from the hotter interior of the star. So the interior of the star could be, hundreds to thousands of times hotter than the outer layer. So as this light is trying to stream through, certain colors of light, certain wavelengths are favored by hydrogen atoms because they use that light, they absorb that light, and the electron jumps up from level 2 to level 3, 4, 5, 6. So this particular dip here that Kevin is pointing to represents a transition of the electron from level 2 to level 4. And because the energy levels within atoms are very specific and the same from one hydrogen atom to the next, same in the Earth as it is in the star, This is an Andromeda, 2.5 million light years away, but same physics. So we can see that that's what that particular dip is caused by. The deficit of photons at that wavelength, the diminution of the number of photons at that wavelength is because they've been absorbed by hydrogen atoms in the atmosphere of the star, and they've used that to send the electron from level 2 to level 4. The next one is level 2 to level 5, and that's called H gamma. Then you see H delta. Then you see H epsilon. The next one is called H8, because if you're counting, it's 2 to 4, 2 to 5, 2 to 6, 2 to 7. And then because people don't remember very much of the Greek alphabet, you can see H8, 9, 10, 11. You can see the very nice Balmer sequence. And because the energy levels get closer and closer together as you march up, so the differences in energy from level 2 to those also get closer and closer together. That's why those lines are getting closer, if that makes any sense. The energy of a photon is directly related to the wavelength of light. So the higher the energy of the photon, shorter the wavelength of light. So in going from level 2 to 8, it requires some energy. 2 to 9 requires slightly more energy, so slightly shorter wavelength. This is called the Balmer sequence. So that's, yeah, what Kevin is zooming in on is H beta, I believe. Yeah, beautiful.
Yeah. And yeah, to keep building on this picture, like Raj just said, as light interacts with the electrons in the orbits of a hydrogen atom, the light that's emitted or absorbed is a perfectly defined wavelength value. So in theory, you'd expect this to be an infinitely thin dip in the light. But what we actually see is a spread out amount of light. And there are a lot of different features that cause this, or a lot of different reasons for this. But some of the ones that are intrinsic to the star are because all of the atoms of the star are moving with speed because of, they're hot, they're bumping into each other. They cause the light to be smeared out a little bit.
Doppler shifted.
So, yes, yeah. And so that causes kind of this spread out effect that you see here. But then there are also effects of the Earth's atmosphere as light passes through it. Some things are basically the light can get bounced around in the atmosphere. The light can get bounced around in the telescope in ways that cause it to get spread out a little bit more than you might predict otherwise.
And rotation could also do that, right? If the star is rotating,
right,
then the part of the star that's directly facing you, that part is not moving towards or away from you, it's moving across. And so, of course, its Doppler shift will be exactly what you would see in the laboratory. But if you imagine a star spinning, part of the star is moving towards you. Let's say, depending on how it's spinning, the right edge could be moving towards you, left edge moving away. So those produce Doppler shifted version of the same absorption line. So the composite of all of those produces width to the line.
Yep.
Now,
okay,
yeah,
we're about to finish on this target, so you'll see us move to a new one. I have a list of all the targets we're interested in, and I've selected this one as the next place we're going. So we're reading out on blue, and we just have to wait to read out on red.
Is the next object also transient in Andromeda?
Yeah, variable.
Variable star, I see.
Yeah. Okay, we are reading out on red. I'm sending coordinates to POCO. And Sean, we are ready to move.
I do not see a target POCO.
Weird. How about now?
I still do not see a new target in POCO.
Okay, that's strange. Send to POCO. How about now?
Still no new target.
Okay. try that. Did that work?
Negative.
Okay, I'm able to send the name, so this is strange.
Perhaps try closing that particular Core tab.
Yeah.
So quit button in the lower right.
Yeah, I've already quit it. I don't know if my
Oh, I see chords in the middle there. Okay.
there we go. Okay. Need to find the right target again. Make sure. Okay, sending new coordinates to POCO.
Now I see new coordinates.
To you, okay. We are ready to move. Okay, and I have a PA of, oh, 1 second, disappeared. I have a PA of 101.
101, got it. And you're now.
Kevin, is the slit narrowed?
I've just narrowed it.
You have, okay.
Yes. Thanks for checking.
Okay, we are on target. Putting it on the slit.
I can open the slit?
No, I'm putting it on the slit now.
Oh, okay.
Okay, you may take the slit back. And you may begin your exposure.
Okay. We will be here for 15 minutes.
Okay.
Okay.
Is that 90 seconds?
Three 300 seconds.
Oh, 300 seconds. Got it. Got it.
Yeah.
Got it. I want to, can I answer one of Zara's questions, please?
Yes.
Okay. So Zara, what I was trying to explain is, so the first letter of your first name is a Z, right? So if you were to imagine you're sitting in your office and you've written on your office door, there's a, let's say it's your office door has a glass window in it. On that, you've written just the first letter of your first name, right? Z for Zara. So someone outside looks at that and say, oh, that's Zara's office. I'm seeing it from the outside. That's looking at a globe from the outside. If you're sitting inside your office, reading that same letter written on your office door, the glass part of your office door, it'll look like a laterally inverted Z. So that's what I mean by parity reversal. So when we look at the Earth's surface, we're looking at a globe from the outside. When we look at the sky, it's like looking at a sphere from the inside. You can, if you think of the stars as being painted onto the celestial sphere, we're looking at the sphere from the inside. So to maintain consistency between the coordinate systems on Earth and coordinate system in the sky, we have to parity reverse. That means that same Z that you see one way looking from the inside versus the other way looking from the outside. So this is what we're doing. The north and east form a proper L, north, up, east, right, when you look at a map of the Earth. But when you look at a map of the sky, it becomes a north and east like that, with north, up, east to the left instead of right. Does that make sense?
I also see a question, how do we decide the exposure time for an object? So I am looking at, so for our list of targets, we also have some helpful resources for I'm trying to bring my screen over. There's some helpful resources for their properties in terms of how bright they've been measured, and based on how bright they are. So this is the document that I have for the current target we're looking at. So we're seeing its light over time, where time is the x-axis and how bright it is the y-axis. And you can see it's kind of been going up and down in terms of brightness, which is why we call this star variable. If I zoom in here a little bit, this is the actual star we're looking at. And down here, you can see the actual measurements, the magnitude of how bright it is over time. And so I generally, to decide the exposure time, we look at its most recent measurement and use that as a ballpark guess of how long we want to expose on it for. But the name of the game is to get enough counts that you're able to clearly figure out, or clearly say that, yes, there is the thing that I'm interested in here. Because if we took a very short exposure, it'd be much harder to do that. But if you took a very long exposure, there are two things to be concerned about. One of them is you might saturate on the target. If it's a particularly bright object and you expose for too long, you might overexpose your CCD so that you get more counts than it's able to handle, in which case you don't get any useful measurements. So that's something to be avoided. And then another thing to be careful of is, and you can see it a lot clearer on the red side here, just spontaneous events such as cosmic rays or radioactive decay of the CCD itself causes these patches to occur. And you really don't want those to happen on top of your science target. And so to guard against that, we take multiple slightly shorter exposures that we can add together later. And because these are random in terms of where they appear, they disappear if we take multiple pictures together. So the name of the game is to do a long enough exposure that you're able to get the information that you want. Short, you don't have to worry about too much contamination from cosmic rays, and also short enough that you're being efficient with your time. Because we could spend all night looking at this target if we wanted to, but that wouldn't be that wouldn't get us anything more than, you know, if we spent half an hour on it. One of the other things I'll point out that we're seeing in these images is so there's physically a piece of metal that is at the front of the telescope that's blocking out all the light except for a slit that's centered on the star that we're interested in, so that you see the star's light as this vertical line here. But you also see these horizontal stripes that kind of look like a barcode. And this is because the slit is this width here, and it is letting in, or it's the edges of the slit are seeing the Earth's sky as well, which is glowing at particular wavelengths. So if I take a slice that's not at the star's light, we see a few really significant bumps all along the way here, and these correspond to emission from the Earth's atmosphere. So it's the sky glow, and so, you know, some of the work that we need to do later on when we're processing this data is to remove the light from the Earth's atmosphere from the spectrum of the star, so that we're just looking at the information from the star. Some great questions.
Sarah, if you could please tell us a little bit about OAE. Is that, you said Office of Astronomy Education from the IAU, right? Is that what OAE stands for?
Sorry, Raja, did you just say something?
Yeah, sorry.
Sorry,
I
so
was
had a call.
asking whether OAE stands for Office of Astronomy Education. Is that what it stands for?
Yes, Office of Astronomy for Education. So, you know, the IAU, the last few years, they've kind of recognized that rather than just, if you like, solely looking at, you know, gathering astronomy knowledge and, you know, professional astronomers, they also need to kind of expand and promote astronomy. So now they have other offices. They've got the Office of Astronomy for Development, Office for Astronomy Outreach, and the Office of Astronomy for Education is the newest one. So they're trying to promote more astronomy at school level.
And that's all over the world, right?
Yes, it's global. I mean, they're setting up this network of the NIEX, the National Astronomy Education Coordinators. So I can't remember how many countries they're in yet. Obviously, they're not in every country yet. They've only been in existence a year or so. But that's the idea, is to have people in each country who can report back on, this is what we do in astronomy in our country. And then if the office has, you know, projects or ideas to disseminate, then it will go through the coordinators. Yeah.
I see. And is the focus uniformly across as many countries as possible? Or is there a specific focus on, say, developing countries?
No, it's everywhere. They want it everywhere. They want them everywhere.
Okay.
Yes, I mean, I would say in Africa, you know, they're still looking for quite a few people. I mean, they haven't filled the coordinator positions for every country.
Every country, okay.
Yes.
Do you think something like this? I mean, tonight we're using a particular telescope and we're doing a particular project, but you know, there's going to be, you know, just our project itself, Shadow the Scientist, this program itself will be offering something close to 40 or 50 sessions between now and the end of the calendar year. And my hope is to keep doing this every, you know, off the order of once a week, even more frequently, because, you know, there's less than 26 weeks left for the end of the year. And I think we'll be offering maybe as many as 50 sessions or something like twice a week on average. Would this be useful, you think, for, you know, it's not traditional education because, yes, we're presenting something, explaining things, but it's not, it's more, how can I describe it? You know, it's not curated content, if you see what I mean. We're doing our experiment and we're talking about it, but it's not rehearsed, it's not polished. Do you think it would be of interest?
Personally, I really do think it would be. I can't even remember exactly where I saw this advertised, but I mean, already, I mean, for me, it's fascinating. As I put in the in my chat, I mean, I did a physics degree, but I'm not a professional astronomer, but I've been doing astronomy education for about 10 years. And, you know, we're always talking about, oh, you know, yes, astronomers use the spectra, but to actually see it happening is a completely different thing. It's really, really interesting. And just the answers to the questions to be giving that sort of detailed explanation of how this works and what it can give you. And to me, it's fascinating. So I think it would be. I would say that so in Ghana, we don't have any at the moment. There's no astronomy degrees. There's no institution offering astronomy degrees. And there's not that much astronomy in the school. But what we do have is a network of a lot of enthusiasts. So I think students of physics who are interested in astronomy, and even though they can't study astronomy in Ghana, they may go elsewhere to do a master's or something. I would have thought this would be really fascinating. And even for the school kids, I mean, we have projects in schools where we do astronomy clubs, again, just for them to see it actually happening. I think it would be great. I mean, I can definitely talk to other people I know, you know, to get their point of view as well. But I think it'd be fantastic.
So, Sarah, I'm thinking that the people in Ghana we've been in touch with have been at Ghana Radio Astronomy Observatory.
Ah, right.
So
Yes,
Proven,
yes.
Theo,
Ah, yes, yes, yes. I know them well. Yes.
Okay, so that's who I was connected to them by one of my faculty colleagues at UCSC. Her name is Nia
Right.
Imara, and she spent
Okay.
part of her
Ah,
childhood
I know
in
her
Ghana.
as well.
You know, okay.
Yes,
So,
she. Well, no, I don't know her. She came and gave a talk at the planetarium. So we had a
fantastic. In
wonderful
person.
event.
In
Yes,
person.
yes,
Wow,
yes,
wonderful,
yes.
wonderful.
I think she came for I think another event, but I can't remember how we got in touch, but she agreed to come and she gave a talk at the planetarium. It was wonderful. Yeah.
Was that a long time ago or recently?
It was a few years ago.
Before the
now we
pandemic.
measure everything as before. Yes, but everything before COVID. Yes,
Exactly.
definitely.
BC and AD, yeah.
Definitely, definitely.
So Nia's been a faculty member at UCSC since July 1st of 2020. So she started during the pandemic, and we've taught some classes together. She and I have, and we're going to teach again together in the
Great.
next year. So I know her, through this collaboration through teaching, but she's the one who's helped make this connection with Ghana Radio Astronomy Observatory.
Okay. Yes. Oh yeah, no, I know Proven well. Yeah, and he's a good contact, and he will probably know more about the university level contacts. I probably know more about the school level contacts.
School level, So for Shadow, we've been inviting anyone who's interested. We haven't restricted it to grade levels or anything like that, or any particular stage of one's academic career. We've really kept it as open as possible. I
can talk to Proven and
that would be good. So the one thing we've been
yeah.
talking about for Shadow the Scientist is, this is an example of an open session where we put the registration link on our webpage and we disseminated it widely. We've also been talking about the possibility of doing a dedicated session. Let's say I'm just going to make up an example where we worked with a coordinator, an outreach coordinator we worked with in Harare, in Zimbabwe, where he invited several schools from Central Africa, some from Zimbabwe, some from Harare itself, some from one school from Malawi. And we were in multiple schoolrooms at the same time in the same Zoom call. So you can imagine one of the connections was from one school in one country, another Zoom connection could be from another school in another country. And in each of these cases, the Zoom video was being projected in an auditorium, and there were maybe 30 or 40 kids sitting in that auditorium, happily missing some boring class in school to do this. But it was the middle of the day, right? Because, just like it is the middle of the day for you.
Break.
So the time difference is actually working to one's advantage.
Raja?
Yeah, sorry.
Okay, I am sending new coordinates to POCO, and we are ready to move. Hopefully they went through this time. Sean, did you get my new coordinates? Oh, is it Matt now?
Very close to the original coordinates. Is this correct?
Probably. I mean, we're all in Andromeda.
Okay. Then yes, I have coordinates. Are you ready to move?
Yes, ready to move. And I have a PA of 9.9. Yeah, all of the targets for the rest of the night will be in Andromeda, so we won't be moving much between subsequent targets.
Very short moves. Got it. Okay, I see your target. I will get it on the slit.
Perfect.
Okay, we are centered. We take the slit back. And we're guiding.
Okay, we will be here for 10 minutes.
Is this another variable star or a transient?
Yeah, everything up until the very last target we expose on will be
Yes,
variable.
variables. Okay. So Sarah, we could do dedicated STS sessions, Shadow the Scientist sessions, where we don't advertise the registration link widely, but we work with one or more organizations that will be part of that dedicated session and invite only those you'd like to invite from that session. If we were working with you on a dedicated session, we'd set aside 2 hours on a particular date. It would have to be a date on which we already have time on the telescope. Those dates are already listed on our Shadow website.
Falling star on the all sky.
That's so cool.
Every once in a while it pops up.
Oh my gosh. It's crazy.
Whoa,
Wish.
I'll bring this over. Oh, come on. Trying to get there before it updates. Shooting star on the all sky cam.
Wow. That is spectacular.
Yeah.
Perseids are peaking next weekend, by the way. Like from Thursday to like Saturday and
What's
Sunday.
speaking again?
The Perseids, the meteor
Perseid
shower.
Perseid
Yeah.
showers, yeah.
Have a little camping reservation for Thursday, so I can go maybe see some
That's
meteor
spectacular.
shower
Perfect.
action.
I'm gonna be back
That's
in
very cool.
Canada next week. Gonna hopefully be somewhere rural.
Pinnacles.
Yeah, Pinnacles is great. I love
Pinnacles is great for this.
But I think I got my reservations for Mount Diablo, which are similar.
Well,
A little closer to me though.
yeah, Kevin, the guider camera is what Zara was asking about. That the purple and
I can go
yellow
back to
colored box that has the compass on the left-hand side. I'm guessing that's the guider image.
Here?
Not that one, but this one. Is this one what you meant?
Yes,
Zara?
that's what I was asking about.
That's the one you're asking about. This is a
Yeah.
small camera that is, it's very cool. So what happens is the telescope focuses light, and that focused light, we want to isolate the light of one star, only the one we are interested in. So we actually have that light go through a piece of metal with a cut in it, with a gap in it. That's called a slit. So that we're not seeing the star that we are studying right now because its focused light is going through that gap. Now, the rest of the metal plate reflects light, and that's what we are seeing as these orange or yellow spots. So it's called a guider camera. It helps the telescope very precisely swing, gently sweep across in order to compensate for the Earth's rotation.
Okay, I see. And so what exactly are those little black kind of spots?
Those are bright stars. Those are other bright stars in the Andromeda galaxy.
Okay. Okay. Thank you.
Sure. No, those are great questions. And Sarah, yeah, we will be doing this into the future, as far as I can tell. So, we have these, I'll put a link in the chat that'll give you a range of dates we'll be working on that's been assigned to us. I'll just find the link and put it in the chat. Here we go. These are the STS dates. Let's see. STS being Shadow the Scientist, STS dates can be found at this link here. And you'll see there are 3 dates in August, of which tonight is the first of those 3, and we're doing 2 STS sessions. We're doing a total of 4 STS sessions in August, 2 on August 3rd, 1 on August 19th, 1 on August 28th. And then we'll be doing this many times in September, October, November, December. So if any of these nights happen to coincide with a date that works well for, let's say, a school group or a set of schools, if there's a particular, we know the telescope schedule months in advance, not years, but months in advance, a few months in advance. So we could easily, I realize it takes quite a bit of organizing and communicating to see, both to gauge interest and to see when students are available and educators are available. But we'd be happy to do it. And one of the things about a dedicated session is what's happening, like on a open session like this tonight, is Zara's on the call, Sarah, you're on the call. We saw, let's see who else is. We have Rafika. I get your name right, Rafika. Yeah, Rafika is on the call. When we had a session a little bit earlier, there were, we had something like 20 participants. We have someone who's just joined. It's a Samsung Galaxy S7. If you wouldn't mind this, feel free to type your name into the chat or unmute and tell us your name. So what happens in these open sessions is individuals connect, individual students and educators connect that's Dr. Shipa. Hello. Well, thank you for connecting. So what happens is then, while it's a great experience for the individuals who connect, there's no follow-up in the sense that you're not connected to the other people on the Zoom call at other times. Whereas if we do a dedicated session in a school, the students who are taking part, there's a common experience, and you can talk about it afterwards, what was confusing, what was exciting. There can be some follow-up, if that makes sense, in a dedicated session. Dr. Shipa, welcome. One of your students is here, and and I saw you sign up on our registration form, so welcome.
Oh, thank you. Greetings, everyone. Thank you very much. It's an honor to attend one of these. Thank you very much.
What subjects do you teach? Am I pronouncing your name correctly? Is it Molet Lanyi?
Oh, yes, yes. The name you are pronouncing it properly, but my surname is Tsipa. It's
Shipa,
not
okay.
She. Yes, yes, it's Tsipa.
Shipa, okay.
Yes, yes. I'm a theoretician, so I teach almost most courses here.
Okay. You're a theoretician in astrophysics or physics?
Physics.
Physics, okay. What area of physics do you work in?
Oh, I'm all over.
Okay.
Quantum mechanics,
Gotcha.
general relativity, stuff like that.
I see. Oh, fantastic. Fantastic. And Lefika is your student, right?
Oh, yes, I taught him a few years ago, but he's doing his MSc right now, but with another colleague of mine as his supervisor.
I see.
He's around. I think he can answer for himself
Yes, yes.
in terms of
Fantastic.
what yeah, the specifics of what he's doing.
That's wonderful. Okay.
I just joined in. I had a problem with my Zoom. Apparently, it needed an update. I didn't know.
Okay.
So I don't know what I missed and how much I missed.
One of the other things we've been.
One second.
Yeah, sorry.
Gotcha. Okay,
Sorry.
we are reading out on red. I am sending new coordinates to POCO, and we are ready to move. Sean, did my coordinates go through?
Yes.
Perfect. We are ready to move.
On the move.
And I have a PA of 9-7.
9-7. Got it. Okay, you may take the slip back. I'm going to position 3 to find something to guide on.
Okay.
And you may begin your exposure.
Okay, and we will be here for 10 minutes.
Thanks, Kevin. This is 3 times 600 seconds.
3 times 200.
3 times 200, sorry. Total of 600, got it.
Yeah.
Um,
Okay, I will step out for a little bit, but
problem.
it looks like you got some good Good questions.
Some
in
good
the chat.
questions here. Yes. So Sarah, it depends on what kind of transient. So exploding stars, things like supernovae, depending on exactly which kind of exploding star, there are a few different kinds of exploding stars. They tend to stay bright for weeks to months, not hours or seconds. They tend to stay bright for a few weeks, and that's set by the half-life of radioactive elements like cobalt, nickel. They're powered by the fission of these elements. So the physical process that powers these explosions, the physical, detailed physical process will often set the timescale for this. There are shorter variations. There are certainly, in general, when you're talking about transients, there's quite a range. There are things that can be, visible very briefly, like novae can be relatively brief, hours or days, not weeks or months. There are things that can be even shorter than that. There are gamma ray bursts that are real, flashes, literally flashes, that are, we're not talking about days, hours, we're talking about seconds. So there's a range. When it comes to stars that vary, that pulse, there's a very interesting correlation. The bigger the star, the longer it takes to pulse. And the smaller the star, the more rapid its pulsation, the more its natural frequency tends to be higher. And a good analogy of this can be seen in the natural world. If you think about the rate at which birds flap their wings, very large birds do very gentle flapping of their wings. Their natural resonant frequency is low. Whereas something like a hummingbird with tiny wings, really small, flaps its wings very fast. You see many examples of this in the natural world where the natural frequency of small things is very high. The natural resonant frequency of big things is very low. So the number of cycles per minute is low. And you see that for stars. You definitely see that for stars. One of the things we've done with dedicated sessions occasionally is, we might do a public talk for the students in either one school or multiple schools. We now live in an era of Zoom, thanks to the pandemic. So we could be connected to multiple school audiences at once. We could do a general talk about astronomy, the kind of questions we're answering. And then this is a deep dive into the details, the technical details. So we could precede it or follow it up with a more general talk. I'll in the chat, I'll put a link to a public talk I gave. It's been a year and a half now, but I give public talks quite frequently. I gave one earlier today, but this recording that I'll send you is a recording from a year and a half ago. It'll give you a less technical but broader overview of the kind of questions I'm interested in personally and our research group is involved in. So I'll take a moment to find the link and send it on. I just put a link to a talk on YouTube that It's a long one. It's like an hour and 15 minutes or hour and 20 minutes, but it's about the research on galaxies, etc. Yes, so we are planning to run Shadow the Scientists on a. Oh, I see. Sorry, you're asking about the follow-up. Yes. So these objects that we're getting a spectra of, they were, before we take a spectrum, they've already been studied by another telescope in California. That's part of California Institute of Technology, Zwicky Transient Factory. They take images night after night, and they look for things. They compare the two images, digital images, to look for things that moved or got brighter or appeared or disappeared or got fainter. So they so that's why you'll see many of the coordinate names have ZTF in front of them. That stands for Zwicky Transient Factory. You can see that in the left column, the object name, there's ZTF at the start. That stands for Zwicky Transient Factory. And BD is actually a type of catalog with bright stars in it. I forget what BD stands for. But ZTF stands for Zwicky Transient Factory. I'll put the name in the chat. Fritz Zwicky was a famous astronomer at Caltech many years ago. That's what ZTF stands for. And look, our goal in Shadow the Scientists is, of course, to showcase the science and the technical side of things. But I think the biggest value we can provide is a human connection. What do astronomers look like? What do they, how do they think? How do they problem solve? I mean, I think science is such a team sport. It's not an individual sport. And I think just getting that point across to young people can make science less daunting, because you don't have to do this alone. You do this in teams. I'm a good example of this. You could see that without the experts on the Zoom call who know what they're doing with the coordinates and the telescope, etc., I'd be nowhere. So I'm heavily reliant on everyone else on the team, so we can make progress on understanding something about the universe. So I agree completely. Yeah. Now, I was personally what turned me towards science, wanting to become a scientist, was watching a video series, a movie series, multi-part documentary called Life on Earth. It was by David Attenborough. Wonderful series, and it should have turned me into a biologist, but it turned me into an astronomer. Yeah, and you're absolutely right. We spend a small fraction of our working hours, doing this kind of data collection. We spend much more time doing the analysis, the removal of the instrumental and atmospheric signatures, analysis, the storytelling, the writing of theory and experiment papers. Our group mostly writes observational astronomy papers. It's only a small fraction. I would say probably only a few percent of the time is spent up, doing the observations. Yes, Lefika, we use, I can speak personally to the telescopes that I am using now. The Hubble Space Telescope, James Webb, this telescope in California called the Shane Telescope, S-H-A-N-E. Later in the year, in September, we'll be using the Keck 1 and Keck 2 telescopes, mostly the Keck 2 telescope on Mauna Kea in Hawaii. These are, so Keck and this telescope, tonight's telescope, are telescopes that are ground-based. They're built on mountaintops. But Hubble and James Webb are orbiting telescopes. They're space-based telescopes. I use a different telescope in Hawaii.
Raja.
Yeah, sorry, go ahead.
Sean, I am sending new coordinates to POCO, and we are ready to move.
Okay, on the move.
And I have a PA of 9.5.
I'm sorry, you have a PA?
Of 9.5.
9.5, thank you. Can we take a slip back? And we are guiding.
Perfect, thank you. We will be here for, what did I say? 3 by 500 seconds. So a little under half an hour. Okay, I'll open the floor back up to you, Raja, and step away for a little bit.
Okay, thanks, Kevin. That's exciting that Botswana is part of the square kilometer array. So Sarah, Zara, Efika, Dr. Shipe, nothing would make me happier than if we could really, if we could engage more students and educators from, really all over Africa in sessions like these, and Chat of the Scientists, dedicated sessions, open sessions. I would personally be happy to, give a talk via Zoom one day, travel there once travel restrictions are a little easier. But I have a couple of special connections to Africa. My wife was born in Lagos in Nigeria, and also my wife's brother, my brother-in-law, lived in he and his family, his wife and daughter as well. They lived in Pretoria for many years. Sadly he passed away in Pretoria, but he was working on sort of AIDS in Africa. And it would be, the skies in Africa are, of course, amazing. It would be, there's, I would love to partner and figure out ways in which we can engage more students, educators, anyone who's interested, really.
Oh, good to hear that, Raja.
Well, thank you.
I
Thank you.
believe we will see some fruitful cooperation between us and you. And
I'd love that.
we've been on vacation also, so we haven't been able to get hold of more students. We've just reopened, so I think a number of students will start to attend more of these sessions. We also have quite a brilliant student. Problem is things like sponsorship or scholarships. Um, we've had a number of good students, but they cannot, even pursue their MSc and stuff like that. The interest is there. Um, the 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 capability is there. Passion is there. That is our main limitation at the moment.
So depending on the academic, which point in the academic journey the student is in, for university students who are looking to do a PhD, especially in the sciences, astronomy, physics, chemistry, biology, for students who are looking to do a graduate degree, most US universities will cover the expenses of the student, will also pay a stipend to the student for their living costs. For most PhD programs, I mean, Kevin is a PhD student at UCSC. He's actually an international student. He's not a non-US citizen. So that's one thing. And then we run a program for high school students where students can get involved in research, the science internship program, and we offer need-based scholarships. So we had a couple of students from Africa last summer. We have a few students from Africa this summer, and based on the family's income, if the student qualifies for financial aid, then we cover that completely. In fact, for the neediest of our students, we provide a stipend.
Oh,
That
that's
would be
nice.
great, Sarah. Yeah.
Oh, that's nice. Hopefully, we'll reason more.
Yeah, sorry, I didn't hear that. Could you say that again, Dr. Shupa?
I was saying, hopefully, we will reason more on this issue of developing students further.
I hope we can do that. Yeah, really hope so.
All right. Thank you very much.
Thank you. The student internship, I'm going to put some links in the chat. The internship program is for high school students specifically. And this is something we started, this is the 14th year. So we started it in 2009. We're just finishing up our 14th summer. It's something called the Science Internship Program. And it's a much deeper dive into science research and in many subjects. It's not just in astronomy. Each student works on one subject each summer. But I'm putting the link to the name and the link to the website in the chat. We call it SIP, SIP for Science Internship Program. And it's a program within the University of California, Santa Cruz. So you'll see those acronyms there. I just put the chat there. This one is specifically, of all the things we offer, this one is the only one that's specifically for school students in the age range 14 to 18. And it's the only fee-based program, but we offer need-based scholarships. And we've only recently started getting students from Africa to apply and be part of the program. This year, for example, we have more than 300 students in the program, but close to I think 66 or close to 70 students are international students. They're not from the US, and another 30 or 40 students are from outside the state of California where we're located. That's the student internship program I was talking about, Sarah, is the science internship program. Kevin's been a mentor for it. Rafael's been a mentor for this program. Rafael this summer, Kevin in past summers multiple times. And some of the spectra we're taking here, the analysis of those spectra is exactly what Rafael's high school interns worked on this summer. So it's not disconnected from the Shadow the Scientist work, but it's a deeper dive into the technical details, learning programming, learning how to apply programming to understand complex data like astronomical data. What I'm going to do is I'll put my email address in the chat. If you're interested in any more details, I can send you more information about these things. And just feel free to drop me an email. This is my email address, and I'll just type out my full name as well. One of the things you could see very clearly from Southern Africa are the large and small Magellanic Clouds. You have to be relatively far, but I mean, the further south you go, the closer to overhead they are. I've seen them from I think from the Schluschluwe game park in, I remember seeing them from there. Oh, thanks, Sarah. I would love that. Oh, that's wonderful. SMC and LMC. So one of my PhD students is doing research on the LMC right now, Large Magellanic Cloud. This is Doug. It's very appropriate because he is from Brazil, so he's from the southern hemisphere. So that he is studying a galaxy that's only visible from the southern hemisphere makes sense, even though he's right now he's in Brazil, but he spends most of his time in California in graduate school. Oh, Cape Town is so beautiful. Cape Town is such a lovely city. One of the things you can see on the white screen, the small white rectangle that says user at Shimmy. You'll see it says starting image 3. Before it says starting image 1, 2, 3. So Kevin started a sequence of 3 exposures, each 500 seconds in length. And you can see that it's counting down how much time has passed and how much time is left. It's getting quite late for us here in California. It's almost 3 in the morning.
Excuse me, Raja, if I may ask a question.
Of course, of course.
Okay. Well, I posted on the chat. Maybe you didn't see it. I was curious because earlier it was mentioned that you sometimes detect radiations with the telescopes, if I remember correctly. So my question was, what type of detectors do you use, and how is the data that you get processed?
Those are great questions, Lifika. So generally, I mostly work with what would be considered optical and infrared astronomy, and we use silicon devices that are called CCDs, charge coupled devices. So in optical, I'm going to put this in the chat, optical infrared astronomy, what is common are things like CCDs, which are called charge coupled devices, and these are silicon devices, silicon based. And then we also use something called mercad telluride, mercury cadmium tellurium, mercad telluride detectors. These are the types we use. That's for as far as what kind of detectors. And then the data processed, typically these are digital data, so they're processed. Python is very common. The Python programming language is used very often. In fact, Kevin helps me and others teach a class on how Python programming works. We teach Python a few times a year, 3 times a year, October, November once, and then once in, we run an entire workshop that lasts for something like 6 hours. We do 2-3 hour sessions typically on a Saturday morning in California, which will be Saturday afternoon in Africa. So that's something, I'll put the link to that. It's called PIAR, stands for Python and Research. We teach Python, but in the context of research. And I'm going to put the name, it's called Python and Research. Now, Rafael's put the details of the detectors that we use, the digital detectors.
Okay, thank you for that. What was I going to say? So with regards to the higher energy radiations, you're then able to determine what it is, looking at the energy. Let's say gamma rays, more intense energy or higher energies, and then X-rays, less energy. That's how you're able to distinguish between the spectrum, the EM spectrum, the radiation that you get rather.
I'm sorry, 1 second. I've got a break in here. I'm sending new coordinates to POCO, and we are ready to move.
Roger that. On the move.
And I have a PA of 9-1.
9-1, got it. Okay, we are centered. You may take the slip back.
Okay.
And we are guided. You may begin.
Perfect. And we will be here for 40 minutes. Okay, back to discussion.
Yeah, so to answer Lefika's question, I think, Lefika, I think it was you were asking about the different kinds of radiation, gamma ray, X-ray, right?
Yes, it was. Yes.
Yeah, you were asking about that. So in general, that is referred to as, someone who studies all of those, say, that would be called multi-wavelength astronomy. Because what has happened is because the detector and telescope technologies are very different for, let's say, gamma rays versus radio waves or other kind of spectroscopy we're doing at optical visible light wavelengths. Because of this, people have tended to become specialized in, a few ranges of wavelengths and work with that kind of technology. But the different kinds that you just mentioned, gamma rays, X-rays, ultraviolet, visible light, infrared, they tell us about different kinds of physics going on in astronomical systems, stars, galaxies, etc. So, for example, gamma rays are very high energy photons, of course, and those are often associated with very high energy explosions, very compact objects. Radio waves, on the other hand, are often associated with plasma, or ionized gas, low density, opposite of compact, very extended and low density. It's studying these different wavelengths allows you to study different physical phenomena is the short answer. I do a little bit of, I pay attention to a little bit of what goes on at other wavelengths, but I'm mostly have spent most of my career working in optical astronomy, visible light, a little bit of with infrared.
Oh, thank you for that then. So then what type of or the telescopes that are used to detect the high energy radiations in the universe, what examples of telescopes would those be? For example,
So for high energy like X-ray and gamma rays, what happens is the
yes.
Earth's atmosphere is opaque to these at these wavelengths. So one has to send telescopes into space to study them. So there are X-ray telescopes that are on orbiting the satellites, like the Chandra X-ray Observatory is one example. XMM Newton is another one. So, and gamma ray observatories similarly have to be launched into space because the Earth, these kinds of radiation, as you know, they're very damaging to humans because they can break down, they can cause cell mutation, they can break down critical molecules inside cells. So it's good that the Earth's atmosphere blocks them, it's opaque, but to do astronomy at these wavelengths, you have to send telescopes into space.
Okay, thank you again.
No. So I know Zara has left the Zoom call, Sarah. So Zara did sign up for STS through the registration form. So I'm able to, so reach out to me, please, if, you know, if you need me to connect the three of us or something like that. I missed what grade. Let's see if Sarah wrote that in the registration form. I think Sarah's in, I think Sarah wrote high school. Oh yeah, did mention, in fact, in the chat also mentioned high school student and junior or senior, so must be close to finishing high school. I'm going to stop the recording of this STS session since we are very close to the time. Sarah, let me answer your question. You said if the target is a transient, which is a supernova, you would see different elements present in the spectra compared to a variable star. In both cases, you'd see elements present. In supernovae, often you see emission lines, very broad emission lines, whereas in spectrostars, you tend to see absorption lines. So in supernovae explosions, often that light that you're seeing comes from plasma that is being accelerated to very high speeds by with the shock front of the star. So you see electrons cascading down in atoms and ions, and very, very high Doppler shifts and high ranges of Doppler shifts. So very broad emission lines is what you tend to see in supernovae. Whereas in stars, you tend to see absorption lines, not emission lines.